Okay, so today we're talking about angular momentum for both point particles and rigid bodies and systems of particles. So let's get right in. So the angular momentum is shown by the variables L and capital L. They are both vectors, which means they both have direction. The units for angular momentum are kilograms times meters squared per second squared, which you can pull out of most of our equations from your physics reference card. Now for a point particle, we've already talked about linear momentum. So if you have a point particle that is translating from one spot to another, and it has some mass, and it has some constant velocity as it's going from one point to another, then the mass times the velocity gives you the linear momentum for our point particle. To get the angular momentum, the first thing we have to do is fix an axis of rotation shown as the origin. The distance from our axis of rotation to the point particle at any given point in time is the position vector shown by R1 and R2. And the cross product between our position vectors and the linear momentum of our point particle gives us the angular momentum for a point particle. Now when we are taking a cross product, then we have to translate our position vectors so that they are tail to tail with our velocity vectors. And the cross product between those two vectors gives us the magnitude and direction of our angular momentum. Once again, when we're taking the cross products, we point in the direction of the first one, curl in the direction of the second vector, and the direction your thumb is pointing gives you the direction of our angular momentum, which is coming out of the screen. So if we have a system of point particles, so not just one, and we want to look at the angular momentum of our system of point particles, then we simply add up all of the individual angular momentums for each point particle to get the total angular momentum for our system. Now let's look at if we have some object or rigid body that is rotating. So if we have our system of point particles and there's no relative motion between the point particles, so they are not moving apart or together, and they are all rotating at the same angular velocity, then we can find the angular momentum for our rigid body or our rigid system of point particles, all rotating about some fixed axis. And the magnitude of our angular momentum is simply the inertia of our rigid object or system of point particles times the angular velocity of that system of point particles. So shown here, if we have a disk and that disk is rotating, then the angular velocity is one-dimensional, it's coming out towards me, and it's about some fixed axis in the middle. So it is rotating with the angular velocity coming towards me or into the screen. So the magnitude of our angular momentum is simply the inertia times the angular velocity. Now there's a great derivation moving from a system of point particles to a rigid body in your OpenStax text, and it culminates with equation 11.9. Now finally, we already looked at Newton's second law for rotation as it pertained to moving objects as they were rotating or as they were moving about some axis in an earlier lesson. We can also write Newton's second law for rotation as the sum of all external torques changes the angular momentum of an object or a series of objects. So if we have a sum of external torques acting on a system, then that torque will change the angular momentum of our object. That's it for today, physics fans. Have a great night.